All right, my friends, I hope that the first thing you noticed about this problem is that while you do see a composition of two functions, the use substitution method that we showed in the last problem absolutely won't work because you could let u equal sine of x, but you don't have a cosine of x dx in the problem for you to have a place to put your du. So hopefully you've ruled that out. And so I do encourage you to make sure that you work through problems between the videos so that you kind of scratch that itch that you otherwise might end up having in the middle of your AP exam. So I'd rather have you investigate things that, we can file under seemed like a good idea at the time, investigate those things up front as opposed to having, that kind of be in the back of your mind as something that you still need to try. So with that said, like what on earth are we going to do with this? So really what you could do is you could hone in on kind of like the problem, like, sad, we have sine to the fourth, we have sine raised to this power, but we don't have any cosine. And so basically we're kind of wishing we didn't have, that, right? So what we could do is rewrite this as, first of all, sine squared x squared, and then, some people think, oh, great, now you can Pythagorean swap, and I don't think a Pythagorean swap would really be helpful. I think you'd notice that if you went down that road, because you just end up having the equivalent problem, but then it's in terms of cosine and it's almost worse. So instead, you're going to find out that you really don't want to have sine squared there. We really don't like having that. And so wouldn't it be nice if we had a way to reduce the power on something like that, and not have sine squared anymore? And so enter the power reducing formula for sine. And so sine squared x can be replaced with 1 minus cosine of 2x all over 2. And then we do have that result squared like so. So from there, I would recommend you just square this out and see what you have. So you'd end up with 1 minus 2 cosine 2x plus cosine squared 2x all over 4, like so. And then I'm just going to go ahead and divide the 4 in, I think, to each of the terms. So like so. Okay. At this point, I'd be really tempted to just think about this as 3 different integrals. And let's just go ahead and do the first couple of antiderivatives, right? Because integrals distribute over subtraction and addition. So what's the antiderivative of 1/4? It would be 1/4 x. For this antiderivative, you could use substitution to make sure that you get the answer right. But you could also, because this is a relatively simple one, you could also kind of, I'm going to copy the constant down. So I'm just going to focus on this part. So you could skip use substitution just by kind of thinking it out. So what would I take the derivative of to get cosine? So the answer is sine, and it would have to have a 2x in there. But when you take the derivative of sine of 2x, you'd get an extra 2 because of chain rule. So you'd have to have an extra 1/2 weighting in front to kind of cancel it out. So hopefully that makes sense as to why I would get that, and I could skip use substitution. Now for this last one right here, I'm going to pull the 1/4 out, and then I'm just going to go ahead and wait until later to worry about what that equals. So there you go. So now for this last integral, I hope it makes sense. I kind of have the same problem that I started out with in this problem, where I have a trig function squared and I don't have its derivative function there for use substitution. So here I am wishing I didn't have this square right there. I wish that I could make that go away. So we're about to use the power reducing identity on cosine squared 2x. And so a note off to the side for this. So the power reducing identity for cosine is 1 plus cosine. And actually, you know what? I'm not going to use x. I'm going to use u. There you go. It's equal to this. So if u is equal to 2x, then I hope it makes sense that you'd end up with cosine of 2 times 2x over 2. So I'm going to end up with, so I'm just bringing all the stuff I've already, all the antiderivatives I've already done. I'm going to bring them down. I'm going to bring the 1/4 down. And then I'm going to replace cosine squared 2x with 1 plus cosine of 4x all over 2. And hopefully that 4 makes sense based on my note over there. Okay, next, let's pull the 1/2 out of that first integral. And notice there's a lot of writing here, but it is a lot of small, it's not a lot of hard thinking, really. It's just a matter of writing it down so I don't lose track of details and frustrate myself and everyone. All right, last integral, my friends. We're going to be able to just do it. You could always use your substitution, or for simple ones like that, you could kind of reason it out in your head. Okay, 1/8 would need to be multiplied by antiderivative of 1 is x. Antiderivative of cosine 4x would be derivative of sine is cosine. You'd need 4x in there. But if you take the derivative of this, you'd have an extra 4, which you didn't have. So you need a 1/4 there to cancel it out. Don't forget your plus c. And then the final answer would be where you've multiplied the 1/8 in and combined like terms. So just think about this for a second. 1/8 x, but then you'd have the 1/4 x to add it to. So what would that be? 3/8 x, I think. And then nothing else is really a like term. So there we go, my friends. All right, so now you'll know what to do if you have an integral and it just has either sine or cosine to an even power inside. Use a move like that. All right, my friends, example 3. You can see we've transitioned from sine and cosine to tangent and secant. So go ahead and see what you can do with example 3 here. Part A, the integral of tangent cubed x times secant cubed x dx. Part B, integral of tangent squared x times secant squared x dx. And part C, integral of tangent squared x over secant to the 5th x dx. Okay, go ahead and see what you can do with them. Spend, I'd say, about 3 minutes, 5 minutes maybe tops on these, and then check in for me next video.